Hello dear students. Today we are going to discuss about Young's double slit experiment in interference of light. As you know, the condition for bright and dark fringes in interference pattern has been discussed in the previous section, that when a crest of one wave meets the crest of another wave, or a trough of one wave meets the trough of another wave, then the displacement of the two waves is maximum, so that the amplitudes of the two waves will be maximum. Then the intensity of the light waves is maximum, constructive interference will take place, brightness results. So we can say here, when a crest meets a crest, so I can just show you the wave pattern like this. So a crest and a crest meets, a trough and a trough meets. If this happens, then when a crest meets a crest or a trough meets a trough, then what will happen? Displacement of the wave, means the resultant displacement of the two waves will be maximum. So I can show you these amplitudes or the displacements get summed up. So amplitude displacement is maximum, so amplitude is also maximum. This is amplitude. So displacement is maximum, amplitude is maximum, intensity is maximum, constructive interference takes place, brightness results. Brightness results. Intensity is directly proportional to square of the amplitude in wave theory. So intensity will be maximum, constructive interference will take place, brightness will result. Whereas when a crest of one wave meets the trough of another, or trough of one wave meets the crest of the another wave, then we can say this is the crest and this one is the trough. If the crest of one wave meets the trough of another, the crest meets the trough, or trough meets a crest. What is the resultant displacement? If the amplitudes are equal, then the resultant displacement will be zero. Means this wave will be moving in the positive direction, this wave will be moving in the negative direction. What is the resultant amplitude? Zero. So we can say here, if the amplitudes are equal, displacement is zero. If the amplitudes are different, then displacement is minimum. Displacement is minimum, amplitude is minimum, intensity is minimum, destructive interference, DI, destructive interference takes place, so darkness results. Darkness results. This is the principle of interference. This is the principle of interference. One should know this idea very clearly before getting into the various interference patterns or interference experiments performed by different people. So this is the key idea. This is what you should know. When you calculate the path difference between the two waves, what am I speaking about? Crest meets a crest or trough meets a trough. Here I am speaking about the path difference between the waves. If there is no path difference, if a crest meets a crest or trough meets a trough, I can say path difference is zero. Phase difference is zero. Phase difference is zero. If path difference is zero or phase difference is zero, then the displacement will be maximum, amplitude will be maximum, intensity will be maximum, constructive interference takes place, brightness results. When a crest of one wave meets the trough of the another, they are said to be out of phase. They are said to be out of phase. Path difference is about odd integral multiples of lambda by 2. You must write 2n minus 1 lambda by 2. So this is 2n minus 1 into pi. This is the condition for darkness. This one is the condition for brightness. These ideas must be clear first. So whenever you speak about constructive interference or bright fringes, then a crest must meet another crest, trough must meet another trough, path difference must be 0 or integral multiples of lambda, phase difference must be equal to 0 or integral multiples of 2 pi. For destructive interference, a crest must meet a trough must meet a crest, then path difference must be equal to odd integral multiples of lambda by 2, which will be obtained as 2n minus 1 lambda by 2. Phase difference must be equal to 2n minus of 1 into pi. Fine. Based on this idea, we are going to discuss about the Young's double slit experiment, which is the very first and foremost experiment on interference. He first observed this interference pattern. So Thomas Young, a British physicist, used an opaque sheet with the two openings marked as S1 and S2. He called it as double slit. The width of each slit is 0.03 mm. Width of each slit is 0.03 mm, and the separation between the two slits is of the order of 0.3 mm. See the measure here, how much fine the dimension is. So he took a opaque sheet, and he marked two openings here. They were termed S1, S2. S1 and S2 are the slits or openings, and the dimension of the slits, width of the slit is of the order of 0.03 millimeter. Separation between the slits is of the order of 0.3 millimeter. See, 0.03 millimeter, separation is 3 millimeter. These two act as the double slits, and the slits are placed in front of sources, monochromatic sources, and the slit S1 and S2 are equidistant from the source. They are equidistant from the source. So the light waves which are spreading out from the source will arrive at the point slits S1 and S2, which are said to be in phase with each other. So these two slits S1 and S2 will act as the coherent sources, which is the basic requirement to perform the interference pattern. See the condition? The two slits with this fine dimension 0.03 millimeter and are separated by a distance of 0.3 millimeter. This is the opaque sheet. As we are speaking about opaque sheet, light will be passing only through the slits and not through the other portions of the sheet. And this is placed in front of the monochromatic sources. Light waves are spreading out. The light waves which are reaching the slits S1 and S2 will arrive in phase with each other because S1 and S2 are equidistant from the sources. So the slits S1 and S2 will act as coherent sources, which is the basic requirement for the study of interference pattern. Now, the waves which are arriving at the two slits S1 and S2 will spread out, and they superpose one over the other. Waves will be spreading out, and the waves will be superposing one over the other, and they will form alternate bright and dark fringes on a screen when placed at a distance, let us say 1 meter. When placed at a distance, let us say 1 meter, a screen is placed. So we can say here, when a screen is placed at a distance of 1 meter, we can say the waves are arriving at waves are spreading out behind the slits S1 and S2. As they spread out, they superpose one over the other. And they form alternate bright and dark fringes on the screen, which is placed at a distance of 1 meter. If the point O is considered, then the point O is at equidistance from S1 and S2. So the waves which are spreading out travel equidistances, arrive at the point O, which are said to be in phase with each other. These wavelets or these wavefronts are moving equal distances and are arriving at the point O, which are said to be in phase. As the waves are said to be in phase, as per the condition, the fringe formed at O will be bright. Constructive interference will take place, brightness will result. And these interference fringes can be seen with the help of an eyepiece, so that we can see the interference pattern using our naked eye. So with the help of eyepiece, we can see the interference pattern formed over the screen. The fringes which are formed over the screen are called interference fringes or interference bands. Either you can call it fringes or you can call it bands. And we can say here, if any one of the slit is closed, then what will happen? There will be a uniform illumination over the screen. Uniform illumination in the sense, there will be no fringe pattern, but there will be uniform brightness over the screen, which indicates that fringes formed over the screen, it is due to the superposition of the waves. Right? This is what the experiment performed. And we are going to bring out a mathematical relation which is going to explain about the formation of bright and dark fringes on the screen. The schematic diagram for the arrangement of Young's double slit experiment is discussed here. Let us say d be the distance of separation between two slits S1 and S2. D is the distance of separation between the two slits S1 and S2. Let us say A screen is placed parallel to the two slits at a distance capital D. At a distance capital D. As I am saying, D is the distance of separation between the two slits S1 and S2. The slits S1 and S2 are going to act as the two coherent sources which are going to produce interference pattern. And the wavelength of the light coming out of the two slits is taken lambda. Wavelength of the light coming from the two slits is taken lambda. Let us say C be the midpoint of the two slits and O be the midpoint of midpoint on the screen. C is the midpoint on the two slits S1 and S2 and O is the midpoint on the screen. As we saw, the light waves which are spreading out to the right of the two slits S1 and S2 will be arriving at the point O, which is equidistant from S1 and S2. So we can say here the fringe formed at the point O will be a bright fringe because the waves arriving at the point O will be exactly in phase with each other. So we can say the fringe formed at the point O is bright. We call it a central bright fringe or central band, central bright band. A central bright fringe will be formed at the point O. Central bright fringe will be formed at the point O. Now, you are assuming a point P somewhere on the screen, which is at a distance, let us say Y from O, which is at a distance Y from O. So, the waves which are arriving at the point P may either be in phase or out of phase, depending upon the path difference between the two waves which are meeting at the point P. As we saw, at the point O, we are very clear that the slits S1 and S2 are equidistant from O. So the waves which are spreading to the right will overlap one over the other and form an interference pattern at the point O, which will be a bright fringe because the waves arriving at the point O is said to be in phase with each other. If the waves are in phase, bright fringe will be formed. Constructive interference will take place, bright fringe will be formed at O. Now, you are arbitrarily choosing a point P, which is at a distance Y from O. We want to know what is the kind of fringe formed at the point P. The waves which are spreading from S1 and S2 will be arriving at the point P, which may either be in phase with each other or out of phase with each other, which we do not know. Either in phase with each other or out of phase with each other. It all depends upon the path difference between the two interfering waves. It depends upon the path difference between the two interfering waves. So, we should first calculate the path difference between the two interfering waves, and further we have to bring out the conditions for brightness and darkness. Let us say the point P is at a position of theta from C. In the sense, when you are marking the point P from C, it is making an angle theta with respect to the horizontal. So it is at a position theta with respect to C. The point P is at a position theta with respect to C. And I can show here the angle OCP is equal to theta. Angle OCP is equal to theta. If angle OCP is equal to theta, this angle is also equal to theta. I am just completing the diagram here. This angle is also equal to theta. S2, S1, let us say this is M. Fine. We shall now speak about the path difference between the two interfering waves which are meeting at the point P. In order to calculate the path difference between the two waves, this is must. Path difference must be calculated first. In order to calculate the path difference, I can show path difference delta is equal to S2M minus of S1M. I'm sorry, S2P minus of S1P. Path difference is S2P minus of S1P. You can calculate the path difference here. Delta equals S2P minus of S1P. And from the diagram, we can show I am dropping a perpendicular from S1 on S2P. I am dropping a perpendicular from S1 on S2P at M. So we can say here, this is the right angle here. We can show here that S2P minus of MP equals S2M equals S2M. This is the path difference delta. This is the path difference delta. So delta is equal to S2M or S2P minus of MP, which is equal to S2M. So we should know what is S2M. We have to calculate what is S2M. So from the right angle triangle S1, S2M, we need to know the value of delta here. This is angle theta, this is 90 degree. So I can write sine of theta equals S2M divided by S1, S2. As we saw earlier, S1, S2 is at a separation D. So we can say S2M is equal to D sine theta. S2M is equal to D sine theta. Let it be. This is equal to delta, path difference. S2M is equal to D sine theta, which is equal to delta. And from the diagram, from the geometry, we can say the point P is at a position theta with respect to C. So in the triangle OCP, we can mark triangle OCP is equal to theta. Also, angle S2-S1M is equal to theta. Angle S2-S1M is also equal to theta because these two are similar. This angle OCP is equal to theta. From the geometry, we can say S2-S1M. Angle S2-S1M is also equal to theta. Now, if the angle theta is small, we can say sine of theta approximately equal to tan of theta, which is approximated to theta when theta is said to be small. How come this is taken? Sine theta approximated to tan theta is equal to theta itself. When you go for sine series and tan series, you can get the idea easily. Sine of x is simply x. So sine of theta is approximated to theta being smaller angles. If theta is small, then you can take this one. So from sine series, you are bringing out this approximation. Sine theta is approximated to theta. Tan theta is also approximated to theta. So sine theta approximately equal to tan theta approximately equal to theta. Now, we can calculate as sine theta and tan theta are equal. I am going to substitute for sine theta as tan theta, and then for tan theta I am going to find out the value here. So I am converting the unknown into knowns. From the triangle, let us say OCP, we can say tan of theta is equal to opposite side is y, adjacent side is, let us say, capital D. So tan of theta is equal to y divided by d from the right angle triangle. So tan theta, I can write sine of theta is approximately equal to tan of theta is equal to y by d. So instead of sine theta, I am going to substitute y by d. So path difference delta is equal to dy divided by capital D. Delta equals dy divided by capital D. This is the path difference between the two interfering waves which are arriving at the point P. Depending upon the value of path difference, the point P may appear bright or dark. We are going to speak about the condition for constructive and destructive interference now. As we saw earlier, the condition for path difference between two interfering waves to produce constructive interference is delta must be equal to 0 or integral multiples of lambda. The path difference must be equal to integral multiples of lambda. So I can write here the path difference for constructive interference I can write delta is equal to small d y divided by capital D must be equal to n lambda. This is the condition for brightness. Path difference must be equal to n lambda is the condition for brightness or constructive interference. So we are going to speak about the condition for constructive interference or the condition for the point P that should appear bright. So delta equals dy by capital D equals n lambda, where n is the order. N can be taken as 0, 1, 2, 3, etc. Why am I introducing 0 here? Because we already saw at the point O, the waves are arriving in phase with each other, producing bright fringes. So bright fringe has already occupied the central point O. So central fringe is bright. So we are marking 0 for constructive interference here. So the order 0 is given for constructive interference. Now, we can say here dy by capital D equals n lambda or y equals n lambda capital D divided by small d. y equals n lambda capital D divided by small d, or I can say y of n is equal to n lambda capital D divided by small d. What is this condition? This is the condition for constricted interference or the point P to appear bright. This is the condition for the point P to appear bright. And this distance y of n gives you the distance of the nth bright fringe from the point O. Distance of the nth bright fringe from the point O, or from the midpoint O on the screen. From the midpoint O on the screen at a distance of yn, which is equal to n lambda capital D divided by small d, you will be getting the bright fringe. You will be getting the bright fringe. Now, we can go for destructive interference here. What is the condition for the destructive interference or the condition for the point P to appear dark? What is the condition for the point P to appear dark? I can say delta equals same dy divided by capital D. This must be equal to 2n minus 1 lambda by 2. What is the necessity of taking this 2n minus 1 lambda by 2? Why should not I take n lambda by 2? As I mentioned earlier, the path reference for destructive interference, for the formation of destructive interference, must be equal to odd integral multiples of lambda by 2. Means it must be in the order of lambda by 2 values. So when you substitute n lambda by 2, for n, if you substitute the order 1, it will be lambda by 2. For n equals 2, it will become lambda, which will be the condition for brightness. So that should not be the condition for destructive interference here, because that is allotted for bright fringes. So you have to take the path reference as 2n minus 1 lambda by 2. We call it odd integral multiples of lambda by 2. Odd integral multiples of lambda by 2. So delta equals 2n minus 1 lambda by 2. What is y here? 2n minus 1 lambda capital D divided by 2 into small d. So this is the path, or this is the distance at which you will be getting the dark fringe. Y equals 2n minus 1 lambda capital D divided by 2d. Here n is the order, which is 1, 2, 3, etc. Find out the difference here. For bright fringes, I am marking n equals 0. For dark fringe, I am not introducing 0, because thing is very clear. Already 0 or 0th order is allotted for bright fringes. So you will be getting only dark fringes from 1, 2, 3. When the order is n equals 1, you will be getting 2 minus 1 is 1, so lambda by 2. 2 into 2, 4 minus 1, 3 lambda by 2. 2 into 3, 6 minus 1, 5 lambda by 2. So you will be getting the multiples of lambda by 2 in the as the odd integral multiples. So you can say here this is the condition to obtain destructive interference, or this is the condition which will give you the point P as a dark fringe. Point P as a dark fringe. And this y of n, I can introduce a suffix here. Y of n equals to n minus 1 lambda capital D divided by 2d is the distance of the nth dark fringe formed from the central fringe O. From the central fringe, if a dark fringe has to be formed, then the distance must be equal to 2n minus 1 lambda capital D divided by 2d. So you can say here, if I can just bring out some values here. If I am considering n equals 0, then what will be the value of path reference here? Delta equals 0. Or always I can speak about the value of y of n. Y of n is equal to 0 into lambda capital D by small d is 0 itself. This is for 0th order. Y of 1 is equal to n equals 1. So lambda capital D divided by small d. Y of 2 is equal to 2 lambda capital D divided by small d. Y of 3 lambda capital D divided by small d. In the same way, if you write the distance of dark fringes, y of 1, y of 0 is not possible here. Y of 1, 2 into 1, 2. 2 minus of 1, 1. So lambda capital D divided by 2d. Y of 2 is equal to 3 lambda capital D divided by 2d. Y of 3 is equal to 5 lambda capital D divided by 2d. Just look at the case here. It is coming as the order of half integral multiples of lambda capital D divided by small d. So if the distances measured from the central bright fringe O is equal to 0 lambda capital D divided by small d, 2 lambda capital D divided by small d, 3 lambda capital D divided by small d, and so on. At these distances, you will be getting bright fringes. You can see here, between 0 and lambda capital D divided by small d, you will be getting half of lambda capital D divided by small d. So, between one bright fringe and another bright fringe, you will be getting a dark fringe as you go from the center. And you can say here, between lambda capital D divided by small d and 2 lambda capital D divided by small d, you will be getting 3 lambda capital D divided by 2d. So, what is the kind of pattern formed on the screen? You can say the interference pattern formed on the screen will have a central bright fringe. On either side of the central bright fringe, you will be getting alternate dark and bright fringes, which are of equal widths and at equal distances, which are of equal widths and at equal distances. So you will be getting the formation of fringes over here. I can show it with a diagram just to understand how the fringe pattern will be formed on the screen. Now we shall speak about the formation of bright and dark fringes. As we discussed earlier, when two waves superpose one over the other, when the crust meets a crust or a trough meets a trough, they arrive at the point in phase with each other. The path difference between the two waves will be equal to n lambda. So brightness will result, constructive interference takes place. That is shown in the diagram here. For destructive interference, we can see here the two waves arriving at this point P are said to be out of phase, 180 degree out of phase with each other. So destructive interference takes place, darkness results. So this explains the formation of bright and dark fringes here. And we shall go on with the interference pattern here. This is the interference pattern which is resulting due to the superposition of two waves. When two waves superpose one over the other, crest of one wave meets the crest of another, resulting in brightness. Trough meets the trough, resulting in brightness. Crest meets the trough, resulting in darkness. Actually, these positions of the fringe from the central bright fringe are marked in the scale here. You can see the diagram over here. Here the central fringe is said to be bright. As you know very well, the central point O is at equidistance from the two slits S1 and S2. And then at a distance of lambda capital D divided by small d, first bright fringe will occur. Then at 2 lambda capital D divided by small d, second bright fringe will occur. In between these two bright fringes, central fringe and first bright fringe, dark fringe will be resulting, which we can show. Actually, we have calculated the path difference between the two interfering waves. If n equals 1, then 2 minus of 1 is 1. We will be getting lambda capital D divided by 2d at this position. Getting 3 lambda capital D divided by 2d and so on. Actually, lambda capital D divided by small d, when added with the lambda capital D divided by 2d, you will get this one. Lambda capital D divided by small d, 1 plus 1 divided by 2. So you will be getting 3 by 2 lambda capital D divided by small d. Actually, half lambda by d capital D divided by small d, 3 by 2 lambda capital D divided by small d, and so on. So when you go from the central bright fringe, you will be first passing through a dark fringe over here, which is represented by a trough, and then you will be coming across a bright fringe, which is shown by a crest at a distance of lambda capital D divided by small d. Then a dark fringe will be resulting due to the path difference 3 lambda capital D divided by 2d and so on. The same will happen on the left hand side also. Minus of lambda means 2d, and then minus of 3 lambda capital D divided by 2d and so on. On either side of the central bright fringe, you will be getting alternate dark and bright fringes on either side, which are at equispaced and are at equidistance from the central bright fringe. The corresponding phase difference is shown here. The central bright fringe will be at the 0th position. You used to call it the 0th fringe. Then these two fringes are termed first dark fringes. Then first bright fringes, second dark, second bright fringes, and so on. This is how the fringes have to be represented. 0th fringe, first dark on either side, then first bright on either side, second dark on either side, second bright on either side, which are existing at a phase difference of 0. You'll be getting central bright fringe. Then at a phase difference of pi, you will be getting a dark fringe. At a phase difference of 2 pi, you will be getting a bright fringe, and so on. So the first dark fringe will be obtained at a phase difference of pi. The first bright fringe will be existing at a phase difference of 2 pi. The corresponding path difference can be shown here. for lambda by 2 values, you will be getting dark fringes. So for lambda by 2, you will be getting first dark fringe, and for lambda, you will be getting first bright. Then 3 lambda by 2, for 3 lambda by 2 path difference, you will be getting the second dark. Then for 2 lambda, you will be getting second bright, and so on. This is how the fringes are formed, and the positions of the fringes from the central bright fringe is given by this scale, and then the phase difference between the waves arriving at those points are represented by this particular scale, and the corresponding path difference has been represented using this scale. Now we shall speak about the bandwidth. Bandwidth is represented as beta. It is the distance between two consecutive bright or dark fringes. So bandwidth is defined as the distance between two consecutive bright or dark fringes. This is a bright fringe and this one is a bright fringe. The distance between these two is said to be the bandwidth. Or you can take a dark fringe and the consecutive dark fringe. If this is n, then this is n plus 1. So this will also give you bandwidth. So I can easily calculate bandwidth here. Beta for bright fringes. I can write y of n plus 1 minus of y of n. Y of n plus 1 can be represented as n plus 1 lambda capital D divided by small d. Minus of yn equals n lambda capital D divided by small d. The difference is lambda capital D divided by small d. So bandwidth for bright fringes lambda capital D divided by small d. In the same way, we can calculate the bandwidth for dark fringes. Bandwidth for dark fringe is also calculated with the same idea, the distance between two consecutive dark fringes. Beta for dark fringes is beta equals y of n plus 1 minus of y of n, between distance between the nth and the n plus 1 dark fringes. So for dark fringe, the distance can be represented as, I can say distance can be represented as y equals 2n minus 1 lambda capital D divided by 2d. Instead of n, I have to substitute n plus 1. So I will have 2n plus 1 minus of 1 lambda capital D divided by 2d minus of 2n minus 1 lambda capital D divided by 2d. When you find out the difference between these two expressions, you will get once again lambda capital D divided by 2d. Means lambda capital D divided by d. So what does this mean? For bright fringe, you are getting the bandwidth as lambda capital D divided by small d. For dark fringe also, the bandwidth is obtained as lambda capital D divided by small d, which means the width of the bright as well as dark fringes are the same. So we can conclude on either side of the central bright fringe, you will be getting alternate dark and bright fringes which are of equal widths at equidistances. Equal widths at equal distances. So a central bright fringe will be formed, then dark fringes, then bright fringes, then dark fringes. They are all of at equal distances and are of equal widths. This is how a fringe pattern will be formed. So what is bandwidth? It is the distance between two consecutive bright or dark fringes. What is the bandwidth for bright fringe? Lambda capital D divided by small d. What is the bandwidth for dark fringe? Lambda capital D divided by small d. Distance and bandwidth are different. When you speak about the distance of the bright fringe, then you have to go for n lambda capital D divided by small d. Distance of dark fringe, 2n minus 1 lambda capital D divided by small d. When you are speaking about bandwidth for bright and dark fringes, you can say it is lambda capital D divided by small d. Whenever you measure a bandwidth, it is the combination of a bright and a dark band. Bandwidth is the combination of a bright and a dark band. When you are speaking about bandwidth, a bright and a dark band must be taken into account to speak about the bandwidth. Now, what are the conditions required to obtain clear and broad interference bands? What is the condition required to obtain clear and broad interference bands? You can just look at the expression here. If beta must be large and broad, then the wavelength of the light used must be larger. Lambda must be large. The wavelength of the light used must be larger. Then the distance between the slits and the screen must be large or greater. The distance between the slits and the screen must be greater. In the sense, slits are there, screen is there. that this distance capital D must be as large as possible. You can increase the distance D, then the bandwidth will be clear and broad. These are the slits S1 and S2. And what about small d here is coming in the denominator. So we can say, in order to get clear and broad interference bands, the distance of separation between the two slits must be as small as possible. As small as possible. D, small d must be as small as possible. Capital D must be as large as possible. Lambda must be as large as possible. What is the nature of the band formed when you speak about the light used when you use yellow light as well as when you use red light? For yellow light, wavelength is less, so bandwidth formed will be less. For red light, wavelength is more, bandwidth will be more. Means width of the band will be greater when compared to the width formed by the yellow light. So we can simply say, for clear condition for getting clear and broad interference bands, we should have a greater value of wavelength. Means the wavelength of the light used must be larger. Then the distance of the screen from the slits must be as large as possible, and the distance between the two slits must be as small as possible. Now, what will happen when you use a polychromatic light instead of monochromatic light? Polychromatic here refers to a light consisting of many different colors. For example, sunlight, visible light consists of FGR, 7 different colors are there. When white light is used to study about the interference pattern, what will be the nature of the pattern formed? You will be getting a central bright fringe. There is no change in it, because all the light waves which are arriving at the point O will be exactly in phase with each other. A violet will be in phase with violet light from the two slits S1 and S2. Red will be in phase with another red light coming from the another slit. So this red and red are meeting in phase with each other, violet and violet are meeting in phase with each other, and all the other colors existing between violet and red also will meet in phase with each other at the point O. So you will be getting a central bright, which is white fringe. A white fringe will be formed. On either side of the central white fringe, you will be getting colored fringes of varying thickness. Colored fringes of varying thickness, because as we saw, bandwidth depends upon wavelength. Violet has least wavelength, red has greater wavelength. So as you move from the central white fringe, you will be getting violet fringe, then indigo, blue, green, yellow, orange and red, and so on. And these fringes will have different thickness, because their wavelengths are different. As you move from central fringe to the extremities, you can see violet fringe, then indigo, blue, green, yellow, orange, red. And all these fringes will be formed exactly at the position of bright fringe. Exactly at the position of bright fringe. And then darkness. Then violet, indigo, blue, green, yellow, orange, red, and so on. This is how the pattern will be formed. So, in order to find out the formation of interference fringes on the screen, first you should calculate the path difference between the two interfering waves. The path difference is y small d divided by capital D. Path difference is delta is equal to y small d divided by capital D. If this is equal to n lambda, then y equals n lambda capital D divided by small d is the condition for brightness. Then if this is equal to, if this path difference is equal to 2n minus 1 lambda capital D divided by 2d, then you will be getting the condition for path difference. So 2n minus 1, I'm sorry, 2n minus 1 lambda by 2 is the condition for dark fringes. So the distance of the dark fringe will be 2n minus 1 lambda capital D divided by 2d. And for bandwidth, beta for bright as well as beta for dark fringes is equal to lambda capital D divided by small d. You should know these conditions when you are speaking about Young's double slit experiment. These are the basic ideas which are related to Young's double slit experiment. So path difference must be equal to y small d divided by capital D. If this is equal to n lambda, then you will be getting the condition for brightness. And we can say the distance of the bright fringe from the central fringe can be n lambda capital D divided by small d. The distance of the dark fringe from the central bright fringe will be obtained when path difference is equated with 2n minus 1 lambda by 2, which is equated to odd integral multiples of lambda by 2. So this is equal to 2n minus 1 lambda capital D divided by 2d. Then bandwidth can be calculated for both bright and dark fringes, which is equal to lambda capital D divided by small d, which indicates that on either side of the central bright fringe, you will be getting alternate dark and bright fringes of equal widths at equal distances. That's all about Young's double slit experiment. Thank you.